Hi everyone, and welcome back to our quantitative data analysis lectures. In the previous lecture, you learned about the different methods of visualizing a variable's distribution using both graphs and tables. You also learned about the use of statistics to describe a variable. In this lecture, we're going to examine the most common statistics, called central tendency statistics. Now, central tendency statistics are designed to describe the typical value within a data set. Generally, as you can guess from the name, central tendency statistics are located in the middle of the distribution. We're going to talk about 3 different central tendency statistics in this lecture. I'm going to show you how to calculate each statistic by hand. But since you have already had a statistics course, I'm not going to go in depth on these calculations. However, there are several supplemental videos on my website that I've created for you to help you walk you through step by step if you would like more guidance. So what are our 3 statistics? Mean, median, and mode. Mean is represented by a capital X with a line over it, which I call X bar. Mode is represented by a capital M with a subscripted O. And there really isn't a standardized representation for median, so I use MDN for short. Let's start with the mean. It's the most complicated of the central tendency statistics, but I think you'll get the hang of it pretty easily. The formula for the mean looks like this. It means the sum of all x values divided by the total number of x values. Let's do a practice problem to illustrate that. Mary wants to find the average IQ in her class. She has 5 students and their IQs are shown here. So we know that the average is found by adding up all of the x values and then dividing by the total number of x's. In this case, the IQ scores are the x values because they are the variable we're interested in averaging. So we add up everyone's IQ scores and then divide by the total number of scores in the data set, which is 5. This gives us 495 divided by 5, which then gives us 99. So the average IQ in Mary's classroom is 99. Not too bad, right? Now here's the issue with the mean. The mean is calculated using everyone's score. So all it takes is one person to mess up the average for the whole group. To illustrate that, let's look at 2 other variations of Mary's class. The first column is the original scores that we just calculated. The second and third column are the same except for one score, Jacob's score. In column 2, Jacob's score is lowered to 10. This lowers the average from 99 to 84. Remember, the average is supposed to be in the middle, but 84 is lower than all of the scores except for Jacob's. In column 3, Jacob's score is increased up to 200. Again, this time his score pulls that average up to 122, which is now higher than all of the scores except for Jacob's. In both of these cases, Jacob's scores is what we call an outlier. This is an extreme score that doesn't represent the rest of the data set. Because of the way the mean is calculated, outliers can have a significant effect on the calculations. This is why we often use the median values instead of the mean. The median is the middlemost value in a data set. It's not a calculated value, it's simply identified. We find the median value by using this formula here. We take the number of values, add 1, and then divide by 2. That gives us the position of the middlemost value. Now, one caveat here is that whenever you divide by 2, you can either end up with a whole number or a 0.5. If the median position ends in 0.5, then we have to do one more step, and that is to average the 2 values on either side of that position. And I'll show you what that means. So let's do a practical example, and I'll show you what all of this means put together. In this example, Julie analyzes the number of car accidents that each of her friends have been in with the goal of finding the median number of car accidents. She surveys 11 friends and finds the following data. The first step with the median calculations is to make sure the data is in order. The good news here is that our data is already in order, so we can create this chart here. The top represents the X values that Julie collected, 0 car accidents, 1 car accident, so on. The second row represents the position of that person in the data set. Since there are 11 people surveyed, position numbers run from 1 to 11. Okay, so what about that position calculation? Remember that it's n plus 1 over 2. In this case, the total number of people collected is 11, so we do 11 plus 1, gives us 12 divided by 2. That gives us the median position of 6. Now, the super important thing with the median is not to stop here. Some students get confused. They forget this is only the median position, not the actual median value. So now we need to look back at the actual data set to see what the value of position number 6 is. Person number 6 in the data set has reported 3 car accidents, so our median value is 3. So let's try that same example again, but this time Julie adds another friend, so her total N is 12 people instead of 11. When we do the calculations, we find that the median position is 6.5. This means that we need to figure out what the values of person number 6 and person number 7 are, and then we need to average them together. So we make sure that our data is numerical order, and we add the position numbers just like we did before. Then we identify position 6 and position 7. These people have reported 2 car accidents and 3 car accidents respectively. Now we use the mean calculation you just learned to find the average between the two. We take the 6th value plus the 7th value, which is 2 plus 3, and then we divide by the total N in the analysis, which is 2. That's going to give us 5 over 2, which gives us a median value of 2.5 car accidents. So there is one extra step when the data set includes an even number of values that we don't have to take when the data set includes an odd number of values. Just something to keep in mind. We can see the advantage of the median by looking back at our example from before. I've rearranged the columns to make sure that the scores are always in order from highest to lowest. We already know that the mean changes for each column, but the median score doesn't have that issue. Up at the top, you can see my calculations for the median position. They tell me that the position value we're looking for is the 3rd position, which is 100 in all 3 columns. So even though Jacob's score is changing up and down, the median isn't impacted. That's why the median value can be so useful when we look at variables that have extreme ranges and have lots of outliers on either end. The final central tendency statistic that I want to show you is the mode. This is the most frequent score in a distribution. Like the median, it isn't calculated, it's just identified. And luckily for us, identification is super simple. All we have to do is look for the number or value that appears most often in the data set. That's our mode. So let's take a look at that example of Julie's car accidents again. If we want to identify the mode in this data set, all we need to do is count up how many times each value is present and determine which is present most often. Looking at the data, we see that one friend reported no car accidents, one friend reported 3 car accidents, and one friend reported 5 car accidents. 2 friends each reported having a 1 car accident and a 2 car accident, and 5 friends reported having 4 car accidents. By the way, you really don't want to be Julie's friends because evidently they really are not good on the road. So what's the most common value here? 4 car accidents. So our mode is going to be 4. Now what about if Julie's accident data looks like this? Then what would the mode be? Well, let's analyze the frequency together. We can see that one person each has reported 0 car accidents, 3 car accidents, and 5 car accidents. But this time, 5 friends have each reported either 1 car accident or 4 car accidents. So, which is the mode? Unlike the other central tendency statistics, the mode can be multiple numbers. So our mode for this problem would actually be 1 and 4. We call this a bimodal data set. Now, a data set can have an unlimited amount of modes. The only instance in which I would hesitate to include a mode at all is if there is an even frequency across all value types. So let's say that every person had set a unique number of car accidents in this data set, so there's only going to be one instance of every value. Rather than saying that every value is a mode, I would say that there's no mode due to the lack of variation between values. Now, one of the super important things about the calculations I just showed you is that even if you can calculate all 3 statistics, you can't always make conclusions from all 3 statistics. Why? Because it's going to depend on the level of measurement of the original variable. This is a really challenging point for many students because it's a little confusing, so I want to walk you through what happens. When you start with a survey question like this, the response options given to the respondent are chocolate or vanilla. When we quantify this survey question, we create numerical placeholders for the response options. So chocolate becomes 1, vanilla becomes 2. Let's say I give a survey to 5 people. When I look at the quantified data set, I see the responses like this: 2 1s and 3 2s. I run my calculations and I find the following. The mean is 1.6, the median is 2, and the mode is 2. But here's the problem. My actual data isn't really numbers, right? So what I need to do first is I need to undo my coding in order to analyze the actual meanings of the calculations. So a mode and a median of 2 become vanilla. But a mean of 1.6, what does that mean? Here's the problem. We can calculate all 3 statistics on any quantified survey question, but we can only interpret the statistic in some cases. It all depends on the level of measurement. This chart here shows you how this breaks down. We can interpret the mode for every variable, no matter what level of measurement. The median has to be ordinal or interval or ratio, which actually makes sense because median is about finding the middle. And how do you find a middle if you don't have rank order? And the mean, well, that's the most picky. The mean can only be interpreted when the data is at the interval rate or the ratio level of measurement from the very beginning. So for my original question, what is the level of measurement? It's nominal, right? The answer choices are categories and they can't be put in rank order. So if we look at my chart here, it means the only statistics I can actually interpret is the mode. So the most common ice cream flavor in my data set is vanilla. I can't make any conclusions about the middlemost value or the average values due to the level of measurement restrictions. And that's something that's really important to keep in mind. In my class, if you can't calculate something, you simply write NA because it's not applicable for that level of measurement. Okay, well that concludes our discussion about central tendency statistics. Join me in the next lecture video as we discuss dispersion statistics.